this video, we're going to be learning about reaction mechanisms. So we have alluded to the fact at various points in your chemistry education that not all chemical reactions occur in a single step. So a reaction mechanism is just what we call the series of steps that a reaction takes to get from reactants to products. Sometimes it does happen all at once, sometimes it is just one step, but most probably, chemical reactions are a series of multiple steps that occur. So each individual step is what's known as an elementary reaction. So these are single-step reactions. Each step in a mechanism must be elementary in order for it to truly be a mechanism for that reaction. So each step in a mechanism is an elementary reaction. And what is kind of special about elementary reactions is for elementary reactions and for elementary reactions only, we can actually write the rate law based just on the stoichiometry of the reaction. Again, this is only true for elementary reactions, for the individual steps in a mechanism, or if you are told that a particular reaction is elementary. If you do not know that to be true, the only way that you can write a rate law is from data like we did the other day. So the stoichiometry doesn't always matter, but if you know that a reaction is elementary, then the stoichiometry is all you need. So the coefficients in an elementary reaction are your reaction orders for each reactant. So for example, if we have the reaction A reacts to form B, and we know that this is elementary, we can write the rate law for this as rate is equal to K times the concentration of A. Since the coefficient of A is 1, and this is an elementary reaction, we know that this reaction must be first order in A. If we have 2C plus D forms E and F, we can write the rate law, if we know this to be elementary, as K times C squared times D. Whatever our coefficients are become the reactant orders. So this 2 tells me it's second order. My invisible 1 becomes an invisible 1 exponent, telling me that it's first order. So for elementary reactions, writing the rate law is super simple. We just need to look at the coefficients and those become our reaction orders. So what this allows us to do is write the rate law for every step in a mechanism individually. And then we'll talk in the next video about how we can use those individual step rate laws to determine the overall rate law for a reaction. One other thing to add, kind of a piece of terminology that's often used with elementary reactions in particular and with steps in a mechanism, is a concept known as molecularity. Is just describing how many molecules should say reactant molecules, are involved in an elementary reaction. So to use our same two examples here, with A forms B, we just have one reactant molecule. So we would say that this is a unimolecular reaction. I'll use a different example. Next, if we have, say, A plus B forms C, we now have two different reactant molecules. We would say that this is bimolecular. One more. 2A plus B forms C. Coefficients count here. This is telling us that two molecules of A are reacting with one molecule of B. So that's a grand total of 3 reactant molecules. Which we call termolecular. And you don't really need to know any higher than that. After those 3, it goes back to kind of the usual prefixes that we use in chemistry of tetra, penta, hexa, etc. So this is just another way of describing an elementary reaction. And the reason why this is useful in some ways is that higher molecularity reactions tend to be slower. And in fact, elementary reactions above bimolecular are not very common because they tend to be so very slow. They do happen, but very uncommonly. So unimolecular and bimolecular are super common. Termolecular and above, not so much. If you're given a mechanism that includes one, roll with it, but it may not be a very practical mechanism. So a mechanism will always be given to you as a series of steps. And I just want to look at an example of a mechanism, something super generic, and talk about a few things that you should be able to do with a mechanism. So let's do Sure, that works. So two-step mechanism here. In the first step, A reacts with X to form B. In the second step, another molecule of A reacts with B to form C and X. So again, just super generic things to kind of get the gist here. So these are our individual steps. One thing you need to be able to do is identify the overall reaction from a mechanism. So all we're doing to get our overall reaction here is adding up our steps. And we always, as usual, want to cancel things that appear on both sides. So if we take everything on the left and add it together, that's going to be the stuff that appears on the left side of my reaction. We're going to take everything on the right and add that together, and that's going to be everything that appears on the right side of my reaction. But we're going to end up canceling out a few things that appear on both sides. So you will notice that B occurs as a product of step 1 and a reactant of step 2. B is what we call an intermediate of this reaction, is something that is produced in an early step and consumed later. So intermediates are not going to appear in your overall reaction because they're created and then they're used up again. So they're not there. They're not still there in the end. We also have X, which appears as a reactant of step 1 and a product of step 2. X is a catalyst. So a catalyst is something that, from a mechanistic standpoint, is kind of the opposite of an intermediate. It's used up in an early step and then reproduced later on. Recreated later. The catalyst is something that is changing or affecting our reaction mechanism in some way compared to what it would look like without the catalyst. But a catalyst is always something that is not consumed by the reaction, so it has to still be there in the end. But either way, it doesn't appear in our overall reaction because it is simultaneously both and neither a reactant and a product. Because it's there in the beginning, it's still there in the end, there is no net change. So those two things are going to cancel out. And what that leaves us with is we have these two molecules of A on the left. And on the right, the only thing we didn't cancel was C. So the overall reaction for this process would be 2A forms C.